Okay, hopefully I'm live this time. I was having a really hard time earlier, and for whatever reason, the stream just dropped, and I'm like, what the heck? So, hopefully it's up and going now. Let me check. All right. So, I'm on Periscope. We got that going. Let me go to YouTube. YouTube is there. Fantastic. That's not a big issue. Should be on Facebook as well. And Twitch. So, double checking on there. You know, for reasons. How are you guys doing? It's been a few weeks, hasn't it? Let's see. Yep. I'm live on Facebook. And I guess I am live on Twitch at the moment. Hopefully. I'm going to check. Yay, nanoparticles. Hello, everyone. I'm live. Yay. I made it. Hey, Nether. Hello, everyone. Hello. So, today, you keep freezing on Periscope. Well, that just stinks. I have the highest amount of internet that I can get for my local provider. But, you know, I do the best I can. Hopefully it works out in the end with all the processing and stuff. So, you guys like my cheetah thing going on here? I put the hood up because, you know, it's cold outside. Hey, Mrs. Snarky. Hello. So, today, you guys voted for nanoparticles, and I took my little 2-week break. And we have another one later. It's freezing on Twitter. Okay. Boo. Boo for freezing and lagging. Hopefully you can hear the sound all right, because the sound's important. So let's go ahead and get started, because we are going to talk about nanoparticles. Woohoo! So you guys, we're going to talk about all the things associated with the nanoparticles. So what does that mean? What are we going to cover? Today we're going to talk about the types of nanoparticles. We're going to talk about how they're used. We're going to talk about how they are useful. Why do we even use them? In current research, there's so much going on about nanoparticles, so I'll touch a little bit, at least on my background. And a lot of the material that I'm actually going to present comes from a website called azonano.com. It's actually pretty user-friendly, and it's also good for lay people. They explain things very well and very simply. So do check that out. And so essentially, what is it about nanoparticles? What are we talking about here when we're talking about nanoparticles? So essentially, nanoparticles are this. They're teeny, 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 tiny structures of different materials in different shapes and sizes, and they all exhibit very different types of behaviors based on their size, shape, and materials. They've been used for all kinds of scientific progress, including medical science, computer technology, and even some progress in electroconductivity on the atomic scale. So it's really cool. It's still a bit of budding research, but stuff has been around for a while. So what type of materials are we talking about when we're dealing with nanoparticles? Well, there's all kinds of materials. We have carbon-based, metal-based, dendrimers, and composites. Now, I had mentioned azonano.com. They are an excellent website. They cover all the types of materials and nanoparticles that are currently used in technology and research. And all of my info from this talk can be found there. It's an extremely comprehensive website, and it's very, very layperson friendly. So if you don't have a massive background in any kind of sciencey stuff, it's still pretty easy to read. So it's not terribly intimidating or anything like that. So do check it out so you can kind of see some cool stuff regarding nanoparticles. So let's talk a little bit about the different types. All right, so carbon-based materials. You and I are carbon-based life forms. Well, that mostly comes from the fact it's made up of carbon. Now, it mostly takes the form of what we call little hollow spheres. So like the Hoberman sphere that collapses on itself and opens up, you can have these hollow spheres. There's ellipsoids, and you might have heard of carbon nanotubes. Now, the spherical and ellipsoidal type of carbon nanomaterials are referred to as fullerenes. Now, the cylindrical ones I had mentioned are those carbon nanotubes. They have all kinds of potential applications to where we can improve things like films, coatings, stronger and lighter materials, and various types of applications in electronics. Now, we normally don't think of carbon, like charcoal, as something that can conduct electricity, but it is a semiconductor on the nano scale. And so this can be inherently kind of cool to use, especially when we get to computer technology. And also, something else to think about. Carbon is biologically friendly. So maybe down in the future, we might see a little bit of carbon types of nanomaterial films to replace different things to help, I don't know, pacemakers, that sort of thing. Since it has a bit of a semiconductor property, who knows? Maybe they'll use different types of carbon-based nanomaterials in living systems in order to help, maybe even go as far as connecting in between nerves. Now, metal-based materials. That's mostly where my background has been in. So these particular nanomaterials, we look at the metal base, we call quantum dots. We've got nano gold particles, nano silver particles, and different types of metal oxides, such as titanium dioxide. Now, a quantum dot is kind of closely packed together. It's like a semiconductor, so it can conduct electricity, but it's also a crystal, and it's got hundreds or thousands of atoms, and whose size is on the order of just a few nanometers to a few hundred nanometers. Now keep in mind, a nanometer is about a billionth of the size of a meter. So essentially, what we can do with these little quantum dots is change their shape, and it also changes how they absorb and release light. And I'm going to talk about that. It's called quantum confinement. I think connecting between nerves would be a pretty cool use of nanomaterials. So what about the others? Dendrimers. Well, those are polymers. Polymers are just many units of something all linked together. So when you think of a polymer, think of like a tree with branches, okay? And all of these different branches are all kind of linked together. Now, the surface of a dendrimer has all kinds of different chain ends, and these can be tailored to do very specific chemical functions. Now, they can also be used for what we call catalysis. Catalysis is kind of getting a reaction to happen. Now, these three-dimensional dendrimers contain all kinds of interior holes and cavities where other molecules could be placed. So if you've got this branched thing that has all of these branches out, and those ends can interact and get chemical reactions to go, you could put little medicines inside those tiny little pockets, those little holes that once they react or interact with a particular cell, they can deliver the drug directly to it. That makes dendrimers inherently useful. Now, composites. Those are essentially what it sounds like. It's composed of different types of nanoparticles all coming together. You might have larger ones with bulk type materials and smaller ones mixed together. So nanoparticles in this regard, they can be like clays, and they're already being added to products that we see. We see this type of composite nanoparticle materials in packaging, in auto parts, enhanced type of mechanical and thermal barriers, as well as flame retardant properties. So composites are pretty freaking useful. Now, the unique properties associated with nanomaterials. There's so many different properties associated with the different types of materials. This makes them very novel for any kind of electrical, catalytic, chemical reactions, any kind of magnetic properties, mechanical, thermal, imaging. So using nanoparticles was kind of what I worked in, was imaging, because you can fine tune them to get them to act a certain way. It makes them easier with spotting with different types of instrumentation. These are all highly desirable types of properties that we would see in commercial fields, medical fields, military, as well as environmental science types of sectors. They can also find their way into more complex type of nanostructures and systems, so they can actually come together and build from a nanoscale to a larger scale. Okay, The Diamond Age by Neil Stephenson, that dealt with nanotechnology. Let me see. Let me try to catch up on some of this. Let's see. All right, is black mold Stachybotrys? Well, we're talking about nanomaterials right now. There you go. All right, so we're dealing with this. New uses for nanomaterials can be anywhere from using these special properties, and using this along with a number of products already have nanomaterials. This possible application that we see in these various types of products is where it continues to grow. So I'm going to show you all the different ways, all the different things that how these nanoparticles look, so you can get an idea of their shapes, because their shapes are pretty cool, guys. Their shapes are really awesome. Is there life on Mars? I don't know yet. I would believe it's possible, maybe on a cellular level. Maybe we'll find fossils on there. Yes, like and share. Woohoo! So I'm going to show you on this. These are just some. I'll just say some. These are not all, but these are some of the different types of nanoparticles that we can see. And this comes to us from aranaka.com. They also work in nanomaterials. So I mentioned nanospheres, capsules, and tubes. These will be all carbon ones. Here's our dendrimers. Remember we talked about the branch trees? That's these over here. They have little pockets in them that we can actually put medicines in and things like that. We can use drug carriers. I've done a little research with that, and I can talk a bit about that in a little bit. Drug nanoparticle conjugates, where we can attach drugs right to a nanoparticle and it can deliver it to cells. We have carbon nanoparticles, magnetic nanoparticles, which makes them easy to detect. Targeted ligand modifying nanoparticles. Well, that's just a fancy word for saying this nanoparticle can attach to a very specific type of, it could be a cell, it could be a protein, but those proteins or those cells are going to interact with the things that are actually on the particle. Here's another one. Here's what we got, different composites here with protein drug nanoconjugates. So essentially these little stars here are going to be our drug, and they're attached to this particular nanoparticle, and this is released, and those particular drugs will release in the area wherever they inject these particular nanoparticles, and usually they interact specifically with a site, so you can have a targeted type of system. Now these up here, liposomes, these are all friendly for life because of the fact that they're made up of what we call a lipid bilayer. So this right here is what we call a lipid bilayer. That's essentially what your cell membranes are made out of. So these are like little packages, and inside this little package, and this is all organic material, inside this little liposome, we can put medications, we can put proteins, we can put RNA, and then your normal cells will like uptake this and release the contents into the inside of the cell, and then that allows the cell to get, you can have instructions on how to make a protein. which could help with illness and initiate immune responses, all kinds of interesting things. So let me address some questions. Woo! Let's see. So, could nanotubes be joined together to form cables that could change length based on electrical charge? Yes, that's very possible, but here's the thing. You don't want to add too much. You want to keep them on the nanoscale and as thin as possible, because the more bulk material you add, the properties shift. And so I'm going to talk about something called quantum confinement, which makes carbon, which is the reason why it makes carbon a semiconductor on that particular level. Quantum confinement is extremely important in nanoparticle technology because of the fact that that is inherently why we can, it makes, one of the reasons why it makes nanoparticles so desirable in various facets of science. So what am I talking about with that? Where did we start with nanomaterials? Well, Richard Feynman in 1959 had an amazing lecture that he talked about, and goes, there is plenty of room at the bottom. And so at the very bottom of the scale of our metric scale, that goes on forever and ever and ever, it seems, at a billionth of the size of a meter, we look at nanomaterials, and they're kind of like our link between macroscopic solids and atomic level type of systems. And so nanomaterials kind of connect the atomic level with the macroscopic level. They have certain properties that make them different from, for instance, a bulk piece of material. So I have Silver Surfer here. Silver Surfer, if he was actually made out of silver, the material, the property materials associated with like bulk silver is very, very different from nanoparticle size silver because of something called quantum confinement. Now, when you look at bulk size silver, you have a large fraction of surface atoms. So most of Silver Surfer's atoms, the bulk of it's going to be on the inside, but it's not going to be on the top. Now, you also have high surface energy, quantum confinement, and you also have reduced imperfections when you're dealing with imperfections in the material. So if we take this onto the nanoscale, we're less likely to have contaminants, we're less likely to have imperfections in the material, where we have a larger amount of atoms, individual atoms available on the surface, as opposed to bulk materials. Now, the quantum confinement effect allows the ability to tune nanoparticles to absorb and emit highly specific but different wavelengths of light. Nanoparticle, pineapple on pizzas. I like pineapple on pizzas. I don't know why people hate on that so much. All right. So let's talk a minute about quantum confinement effect. That sounds so terribly sciencey and extremely important, doesn't it? We see this happen when we take the particle is too small to be comparable to the wavelength of the electron. So in order to understand this, there's a little bit of science we've got to understand and cover when it comes to wavelengths and electrons. It's something called spectroscopy. Every single element on the periodic table has what we call spectral lines. And these particular lines all show up, and they're highly specific to the electrons associated on the outer shell of the atom. Okay, so if you can think of an element like a solar system, the center is the nucleus. That's where our protons and neutrons and electrons are. That's our sun. And then the different rings that go around it are the different planets. That's kind of what we call the Bohr model. So when we get to the outermost rim, like Pluto and Neptune, all right, that's where the action happens in an atom. So when light comes in and it hits an electron, that electron gets super excited and it jumps up to a higher energy level. But atoms are very specific on what types of wavelengths of light cause them to jump up. Now, how do we know that there's different types of wavelengths of light? It's based on colors. Red is a different wavelength than blue. So this is why we're able to determine what atmospheres are like on other planets based on the colors that are coming at us. So certain elements will have maybe red, green, and blue. Others might be yellow and blue. And you might have another one that's violet, and orange. And those are the lights that are coming at you. That has to do specifically with a certain amount of energy. Well, when we get into quantum confinement, that all changes. So normal spectral lines that we would see from Silver Surfer, we blast him with light. He's going to reflect certain colors back to us based on those electrons jumping up and down. We can change what colors they are based on how big the nanoparticles are. So we can shrink them down and change the colors. We can make them bigger and bigger and bigger just by changing the shape, the size of nanomaterials. We can kind of tweak what colors come out at us. D orbitals. Andy, you know I hate D and F orbitals. The valence shell of the electron moves to define the frequency. Yes, so the movement changes. So what happens is, what we have to do is consider, like, we got to break the words like quantum and confinement. So confinement in this regard means to confine the motion of the randomly moving electrons and restricts it to a specific level. All right? So the quantum reflects the atomic realm of the particle. So as we decrease the particle size to reach the nano 1/1000th of a meter scale, it decreases in confining the dimension and makes those energy levels discrete. This increases or widens what we call the band gap, and the band gap energy also increases. So we're able to kind of tweak it. Sorry, F orbitals. We're able to kind of tweak nanoparticles, and based on the size, we can change which wavelengths they absorb and emit. So that's inherently useful for a lot of reasons, and I'll get into that in a second. So here we go. This is a pretty cool GIF image that I like. This is showing us how as we shrink down in size, the colors can change. And so the electrons are limited to the space that they can actually move. So instead of allowing this larger amount of space for the electrons to move around, we shrink it down a bit. And by shrinking it down, this kind of essentially changes the wavelengths of light that affect it. So reducing the size of materials to the nanoscale changes the amount of energy needed to excite the electrons. Thus, the nanoparticles can be easily fine-tuned to absorb specific wavelengths of light. How cool is that? I think that's pretty freaking groovy. All right. So, why is this important? It's okay, I'm with the bandwidth. Why is this important? Well, it allows specific, repeatable, and custom ways exclusive to a singular purpose for scientists to detect nanoparticles. For example, one wavelength means that particular size of particles are present. These particles can then be used as a beacon to detect other harder to find things, like certain types of cancer, certain types of cells, exosomes, which are released from cells. They're even smaller. You have to ultracentrifuge in order to get exosomes. And even then, the little pellet that's supposed to be at the bottom is invisible. So that's how tiny we're talking. So proteins, we can use this to find proteins in any other thing that the nanoparticle can interact with. So it is especially important in the medical science field for drug delivery and detection of drug delivery to specific hard-to-reach types of drugs like cancer tissues. There's a lot of research that's coming around and going about the use of nanoparticles in targeting drug delivery type of systems instead of like a holistic, zap you with chemotherapy, radiation kind of thing, which can make all of you sick, but instead possibly making nanoparticles to target the cancer and the tumor by itself, so that way you have a targeted treatment as opposed to a body-wide type of response. Another thing, detection of hard-to-find things. So the other tiny things that are not detected with current methods. So you have to think a lot of cancer detection has to do with looking at the cells. Well, what if something is smaller than a cell? What if something is just the presence of a protein? Well, there are certain tests that look for just that protein, but it has to interact with a separate thing, or be known to interact exclusive with that particular material, and that can cause false positives for things. So if you're able to detect things using nanomaterials and they're highly specific and interact with a particular thing, that is like way, way more useful. This could have forensic applications at crime scenes, especially when you start thinking so there's lots of different ways this could be used at a crime scene, especially with nanomaterials. But I know it's seen a lot with detection of hard-to-find things such as exosomes, which I will talk about here in just a minute. Nano is still larger than Planck. Well, this is an interim between the atomic world and the macroscopic world. That's nanoparticles. It's kind of like a bridge. So let me show you about what this looks like. All right. So here's a pretty cool graphic here demonstrating a bit of what we're talking about. So these are spheres. So these are nanospheres. And so by reducing the size, so we're looking at what we call the quantum confinement effect. So just by changing the size, you change the wavelength and color that these particular nanoparticles absorb. Hey, Stephen. And in this particular case, these are what we call the quantum dots, and they are at the angstrom scale. So quantum dots are pretty cool. That's kind of where a lot of this research started a bit, was playing around with quantum dots. And I mentioned that they're just like either a few atoms or, hundreds or thousands of atoms all put together. But as you shift the size, the colors that they absorb change. So if you're able to tag a nanoparticle with a highly specific type of antibody that can target a certain type of cancer, you can use these nanoparticles and detect cancer on a much smaller level. Buckyballs, yes! How does the Doctor fit in all of this? Are we talking about Doctor Who? Are we talking about Doctor Who? That's a good question. Doctor! Oh, goodness, you guys. You guys playing with flat earthers again. All right. So I've shown you a picture of all the types of different nanoparticles. So I'm going to get into a bit more information about very specific ones. Again, if you go to azonano.com, you can find all kinds of resources associated with nanomaterials. So they can be classified into different types according to their morphology, physical and chemical properties, their size, their materials. Some of them are carbon-based nanoparticles. We also have ceramic, metal, semiconductors, and polymeric, as well as lipid-based. So the lipid-based are like the liposomes that I mentioned earlier. So we're talking about carbon-based. The two main materials are the nanotubes, which are called CNTs, and fullerenes. CNTs are pretty much just graphene sheets, like single atom thick graphene sheets rolled into a tube, kind of like a holy straw. These materials are used primarily for structural reinforcement because they are 100 times stronger than steel. Who'd have thunk, right? So they're pretty strong. Now, these CNTs are also classified as single-walled carbon nanotubes, SWCNTs. So we got carbon nanotubes, and then we have single-walled carbon nanotubes. Now, these particular multi-walled carbon nanotubes. That's MWCNT. So you have single-walled and multi-walled. They are pretty much unique in the ways they're also thermally conductive. So they can deliver and conduct heat, which is really, really, really kind of cool. Along the length, and non-conductive across the tube. So across the tube, they are not conductive, but along the length of the tube, they are. And we can put them side by side together and just kind of continue that conductivity. Fullerenes, they're kind of like what we would consider the allotropes of carbon. They look like a hollow cage of about 60 or more carbon atoms. The structure of C60 is what we call Buckminster fullerene and looks like a hollow football. You know, like it could be a soccer ball that's hollow. So the carbon units here, they have a pentagonal and hexagonal arrangement. There are lots of commercial applications because of the fact they also can conduct electricity. Super freaking strong. They're used for structure and also the electron affinity associated with that, because guess what? Carbon binds with pretty much everything on the periodic table. There you go. So let me catch up on some questions. Could this technology be used to remedy the plastics problems in the oceans? Possibly. I'm not certain how plastic would interact with the carbon, but that might be a good idea. Can this have computer applications? I am stupid with all this. I mean, asking for a friend. Oh, thank you, Andy, for the link. I imagine it can, since it is a conductor of electricity. Very possible. And we know silicon is actually in the same family as carbon. It's just one step down. So if we're looking at making quantum computers and computers that can conduct on a teeny tiny little scale like that, it's very possible we could be using carbon for, you know, making microchips. And yes, our national labs figure this stuff out. We're amazing when we work together. I agree. Have you guys seen the NASA video of Winds on Mars? Not yet. So now let's talk a little bit about ceramic nanoparticles. So their growth is kind of similar to the other technologies that we've seen. They're essentially inorganic solids made up of oxides, carbides, carbonates, and phosphates. So this is stuff Andy would like because he likes the inorganic stuff. So this section is for you, Andy. So they have a high heat resistance because they're ceramic. And they also are chemically inert, so they don't do anything to living systems. They have applications that we can see in what we call photocatalysis. Photocatalysis allows the use of light in order to initiate chemical reactions. There's also photodegradation of dyes. Well, sometimes when you use a dye, you don't necessarily want it sticking around, so this allows the use of light in order to get rid of those dyes. And it's also being considered for drug delivery and imaging, so we can use it in imaging, meaning we can connect it to other things that we're trying to find that are much smaller, and it lights up. When we get into metal nanoparticles, we also have something called plasmon resonance, which I can touch on when I talk about the research I've performed. All right, so I do know that plastic is made out of petroleum, so possibly, yeah, you know, we might could do that. Alrighty, inorganics, all I know, being Precambrian rocks. So, when we're trying to control various characteristics of ceramic nanoparticles, we can control size, surface area, porosity. We can change the surface to volume ratio, which is inherently important, especially if we want to carry things in them. They perform as good drug delivery agents. These particular nanoparticles have been used effectively to deliver drugs for different types of diseases, including bacterial infections, cancer, glaucoma. It has lots of different applications in the medical field, and also the fact that it is chemically inert in the body. It doesn't do anything to people, so it's quite useful for that. Metal nanoparticles, my jam. Metal nanoparticles are prepared from metal precursors. I actually have a video to show you how silver nanoparticles are made that comes from us from Wisconsin MRSEC. So I'm going to show that video to you in just a minute. You have so many nanotube jokes running through my head right now. None of them are safe for work. Oh, Mrs. Snarky. So when we're dealing with metal nanoparticles, they can be synthesized through chemical, electrochemical, or even photochemical methods. So we can synthesize them through adding electricity, through interactions of different compounds, and also by blasting them with light. So, for instance, in chemical methods, the metal nanoparticles are obtained by reducing the metal ion precursors in solution. So you start out with a solution that have the metal in ionic form, and you reduce that with chemical reducing agents. Now this has the ability to absorb small molecules and have a high surface energy. So that's kind of what we're looking for in metal nanoparticles. They have applications in research areas with detection and imaging of biomolecules in environmental and bioanalytical applications. They can be detected through what we call plasmon resonance because of the fact that certain metals have a specific signature. That's another thing. Not only do they reflect a certain type of light, but you can also detect them in different ways. So things that you wouldn't be able to see so well, like teeny tiny little proteins and stuff like that wouldn't be able to pick up so well. You can actually coat nanoparticles with different things. They'll attach to those proteins. They'll attach to cells. They'll attach to exosomes. And then, since it's gold, since it's silver, or whatever type of nanometal you're using, you blast it with light. Boom. There. You're able to say, yes, this is attached to the thing that we're looking for. Oh, goodness. So that makes metal nanoparticles inherently used for that, especially in detection and when you're trying to get a good picture of a particular biomolecule, like a protein that's hard to find. So gold nanoparticles are used to coat the sample before analyzing in what we call scanning electron microscopy. This enhances the electronic stream, which helps us get really good scanning electron microscopy images. So, this is all pretty neat. We're talking about metal nanoparticles. Now let's talk about semiconductor nanoparticles. Woohoo! Semiconductor means it kind of conducts electricity, but it doesn't get all crazy about it like metal. So it has properties of what we call metals and nonmetals. These particular particles have all kinds of wide band gaps, which tuning shows different properties. So I mentioned that we can change those band gaps in order to get them to release light in different ways. Let's see. So they're used, like I've mentioned before, photocatalysis, electronic devices, photo optics, and water splitting applications. So silicon is a perfect example of a semiconductor, and we use that in all kinds of technology. Let me catch up with some questions. Do they have a resonance? Well, metal nanoparticles do have what we call plasmon resonance, and so we're able to see that. Richard said something. What did Richard say? I missed it. Oh, goodness. I'm sorry. I'm sorry, Richard, about the plastic stuff. That kind of sucks. Let's see. Can't help but wonder how this knowledge can help with forensics and crime investigation. Well, if you're looking to detect any type of protein, if you know the killer has a particular... Oh, that's the thing. It's just... I'll have to sit and think about that, Mrs. Snarky. Because that's really, kind of interesting. If you're trying to detect something that's hard to detect, but you know that the nanoparticle will interact with that one thing, you can coat any nanoparticle with some kind of binding type of compound that can bind to the thing that you're looking for. But, I mean, DNA is pretty freaking... That was a huge, huge step forward in crime scene investigation. And if you find DNA at a crime scene, coupled with other evidence, that alone isn't enough. You have to have other evidence that points towards that. But that was a huge jump forward in crime scene investigation. Let's see. Will the plastic nanoparticles everyone is eating hurt us? There's nothing that shows that it will. So, it's all right. All right, so let's talk a little bit about polymeric nanoparticles. Now, they're organic-based nanoparticles. So these are kind of like, let's see, the polymer, they have structures that are shaped like nanocapsular and nanospheres. So these are kind of like our little nanospheres. So they have a matrix-like structure, whereas the capsular particles have more of a core shell type of structure. So the active compounds of the polymer are kind of dispersed, like in the spheres, they're dispersed evenly. But in the core shell one, the active compounds are confined to, surrounded by the polymer shell. So if you have like a drug with the polymeric nanoparticles, if it's in the sphere, it's going to be all on the inside and easy to get to. But in the core shell, the drug is just going to be on the outside within that shell. Now, some of the polymeric nanoparticles that we're looking at, they have what we call controlled release. So you might have heard that before with other types of medications. So they release the drug over time into the system after you take it. It's like a slow release. So that's what we call controlled release. It also can have the protection of drug molecules. It can combine therapy along with imaging. So not only can it deliver medications, but we can also get a signal from it with different types of instrumentation. It allows for specific targeting of the diseases or the disease tissue, as opposed to holistically making a person sick like chemotherapy might do. It's highly biodegradable and super biocompatible, which makes polymeric nanoparticles highly desired in research, especially for drugs and that sort of thing. All right, so lipid-based nanoparticles. These are our liposomes, okay? So they're generally spherical shaped. So they look like little, have you ever dropped oil into water and they make those little bubbles? That's kind of like what a liposome is. They have a diameter of anywhere from 10 to 100 nanometers, and it's pretty much got a solid core made of lipids and a matrix-containing type of lipophilic molecules. So on the outside is kind of what we call a lipid bilayer. Now, the external core of these nanoparticles is stabilized by surfactants and emulsifiers. These are all fancy-sounding words, but what happens is oil is scared, it's scared of water, so it's hydrophobic, so it attaches to itself. So it's really easy for these liposomes to kind of form into these little balls. Now, the type of field of nanotechnology for this is far from being saturated. It's still budding and brand new. But over time, there should be a lot of growth with this because of the fact that lipid-based nanoparticles can actually be eaten up by cells. Hey, Godless Island. So I want to say a shout out to several patrons out in my chat now. Andy, Steven, Godless Iowan. I think Richard is one of them. There's several Richards. So hello everyone. So thank you guys for contributing to my work. So as I was saying with like lipid-based nanoparticles, cells can uptake these liposomes, and then that releases the medicine and directly into the cell, which is quite a useful thing to be able to do. So I'm going to talk about how these things are made. So how are these things made? Here's a really cool animated GIF. I don't know of a nanoparticle that looks like this, but metal nanoparticles are very easily synthesized. It doesn't take much. You take a bit of your seed stock. It's what we call a seed stock. And then from that seed stock, you have the various ions. And by incorporating different types of solutions, you can actually cause them to kind of come together and form spheres, rods, popcorn formations. You can make nanoparticles shapes just by tweaking what is inside your solution in order to get them to form a certain shape. It's actually pretty interesting. Actual footage of oil being scared of water. Oh my goodness. So you guys want to see a really cool video about how to make nanoparticles? I'm losing my hood. See, it's cold outside, so I've got to stay warm. Role in quantum or medical tech? I think it has a good role in both. So with the medical tech, I had mentioned before and that was my background, was medical technology. And I'll talk a bit about the research that I've done involving nanoparticle rods and a breast cancer test. So let me show you this video on how silver nanoparticles are synthesized. And this comes to us from Wisconsin MRSec. So check this out. I'm wondering if you can hear me. All right. I'm going to explain a bit what's going on here. Hopefully you can hear me. All right, so what they're doing essentially is this. The formation of silver nanoparticles here is observed by a changing color, since the small silver nanoparticles are yellow. So when they come together, remember we talked about different wavelengths of light shifting what it absorbs and emits when you change the size. Well, in this case, this particular size is yellow. So a layer of what we call absorbed borohydride anions, those are negatively charged boron and hydrogen ions together, on the surface of the nanoparticles, keep them separated so they don't clump up together. So when sodium chloride is added, the nanoparticles aggregate and it turns to a cloudy gray. Now, the addition of a small amount of what we call polyvinyl pyrrolidine will prevent this aggregation so they don't stick together. Yay, you can hear me. So that's essentially what's going on in this video. So is it on loop again? Are we seeing it twice? Because I was reading information. Oh my goodness. So I wanted to explain a bit what was going on over there. So here in this step, they're adding a little bit of heat and it's spinning. So when they add that together, it's going to start the formation of it. So the adding of the different chemicals allows it to form and interact with themselves to make a specific shape. And the shape dictates what wavelength is absorbed and emitted due to quantum confinement. Yay! We don't put food in toaster ovens that are used for that. Some silver nanoparticles being served up here shortly. You add a bit of heat, and now you end up with these awesome, like there's the sodium borohydride. There you go. And that is the silver nitrate, which is the seed stock. And that prevents it from aggregating. All right, guys. Woohoo! So that's how essentially, it's so easy to make metal-based nanoparticles. If you just have the metal ions and you have the correct chemicals, you can kind of tweak it to the size that you want. And you can verify the size of the nanoparticles by using electron microscopy to not only characterize how large they are, but also the shape. So that's one way that you can characterize the size of the nanoparticles and make certain you got the right one. And also what color the solution is. That's also a good indicator on the size of your nanoparticles. Toaster ovens are quite good for many things. All right. So the other things I want to talk about. When it comes to research, gosh, nanoparticles have such a vast spectrum of use that discussing them all here would take hours and hours and hours, but my background is in gold nanoparticles. So I'll take a moment to kind of discuss my research I've performed. Also, if you want to learn about stuff not my research, you can find out more info at azonano.com for the latest news and research in all things nanoparticles. So I was on a paper. I actually have the paper around here somewhere. It's detection of cancerous exosomes through the use of a 3D printed miniature device coupled with gold nanomaterials slides as well as nanoparticles. So essentially, the research that I was involved in involved isolating samples from different patients. So what we would do is we modified a gold slide with a type of polyethylene glycol, which allowed exosomes. Exosomes are kind of tiny like those liposomes, and cancer cells release them into the bloodstream. Now these exosomes contain DNA, they can contain DNA, they can contain RNA, they can contain cancer-related proteins. They can have all of these different things. So other cells, and it has been linked to how cancer cells spread. So the whole idea is being able to detect those exosomes. So even if you can't find a cancer cell, if you can detect the exosomes, then that means the cancer's present and it's trying to spread. So we work to develop a test to be able to detect exosomes from blood samples of various cancer patients. So essentially, we coated the gold slides with a type of polyethylene glycol. Then put our 3D printed miniature device on the top, injected exosomes into those little wells, washed it off, and the exosomes will stick to that polyethylene glycol. Then we go back, put our top back on again, and then we inject nanoparticles that are coated with antibodies that stick to the exosomes. Now those nanoparticles are involved in what we call plasma and resonance. So we could pick it up with infrared spectroscopy, but it also shows up on what we call dark field microscopy. So not only could we detect cancerous exosomes, teeny, even smaller than a cell, with nanoparticles, we could detect it through IR spec as well as microscopes. So you blast it with light, it lights up, that means they're there. We also characterize the exosomes through what we call fluorescence. So that's a little bit of the nanoparticle technology that I have been involved in on a paper that I did with my graduate research. Science! Yay! So I figured I would focus a bit on that type of nanoparticle tech, but there's so many different types of uses when it comes to that. How are the different size and shape nanoparticles first arrived? It's probably just through trial and error. Can nanoparticles be small enough to be impacted by quantum entanglement? No, I don't think so, but they do get involved in what we call quantum confinement. So we're able to tune what wavelengths they absorb and emit based on the size, because the electrons are brought down to such a tiny level, they have less space to move around. And so we can tweak that size, and that changes the color of wavelength that they absorb and release. So there you go. Science, yay! Let me make certain I read everything. Oh gosh, people misspell my name all the time. Man, people misspell my name all the time. Gosh. Man, some people call me Melody. They put an N, and it's just weird. So I don't take offense anymore. So that's what we've been talking about essentially this entire time, has been all the things to do with nanoparticles. How cool is that? This has been an awesome chat, and this has been a flat hour. Quantum confinement sounds like the tiniest jail ever. I agree. So we've talked about the types of nanoparticles, types of research associated with it, the uses for it, the materials associated with it, all the different chemistry related to why we like nanoparticles. They are so freaking cool. I keep dropping a bit of that. What about quantum leaping? Oh, I thought that was through the Ziggy device. So that's what we've been talking about. I'm going to take a moment to thank my patrons. James, Jen, Carl, Melanie, Patrick, Daniel, Stephen, Paula, Carrie, Cersei, Keith, Duke, James, there's another James, Andy, Zachary, Tony, Bo, Stephen, Sarah, Chris, Graham, Dragnot, Godless Iowan, Jennifer, Richard, Doc, Fearsome, and Neil, my 2 newest patrons. Thank you. And Andy recently upped his contribution. Thank you for that. Oh, goodness. I'm so glad you guys enjoyed this talk. Where can you find me? Everywhere on the internet. ScientistMel.com. I have articles as well as all of my slides and information there. If you'd like to help me out and sponsor me, I'm on patreon.com/ScientistMel. I'm working on a couple new shows, and Andy is going to help me with Spirited Science and revive that thing. And I'm working on a new show right now called This Week in BS, where me and Katie Paulson talk about This Week in Bad Science. And I'm also on Facebook. Hit me up on Twitter. My sources, really quick. This was so comprehensive. Check out aznano.com and also aranca.com. And there's also a lot of information on NCBI or NIH. Just type in nanoparticles and medical research on NIH or NCBI. Essentially, the website for that is PubMed, and you will find all kinds of information associated with that. So, you just finished with the Aaron Ra debate. Sam will never make it home if you don't talk about it. Quantum confinement at the nanoparticle jail. I hear the electron coming. It's rolling round the bend. And I ain't seen bulk material since I don't know when. I'm in nanoparticle jail. Quantum confinement's got me. And those electrons keep rolling and change their wavelengths. See. Boy, that was a stretch. There you go. You even got a little song, too. I'm so glad you guys enjoyed this topic. Great show. You're listening the whole time while working on other things. That's fantastic. So, you guys have been so much fun. I'm trying to remember what next week's topic is. I'm going to start bringing back my 1-minute trailers. I really like those, and I have an app that makes my little 1-minute trailer, so I'm going to start making those again to kind of get you pumped for the next show. So that'll be fun. Oh my goodness, you guys are so funny. You guys are so funny. Oh goodness. Well, I guess this has been a flat hour, so. It's been a flat hour. It's over. Yeah, it's been a flat hour since I've been talking with you guys. If you have any kind of questions, you can always ask me on Twitter. You can leave it in the comments on YouTube. I'm also on Facebook. Hit me up at any time. And if anybody's curious to read the paper I'm on, feel free to shoot me a message and I'll send it to you. It's really cool. I like doing the science. And now I'm back doing SciComm and boosting literacy as much as I can. It is my goal eventually to do this as a full-time job. So if you can contribute, if all of my followers on Twitter just gave me $1, I could tour. That's my goals, is eventually to have like science communication conferences where people can get together and share the joy of science. And I would like to be able to visit and do talks in different cities and engage people. So I'm steadily building up with that, and sometimes that takes time. So I do thank my patrons for your continued support. I am on PayPal if you want to do a one-time donation. That's also cool too. So thank you guys for being here. This has been the science of the nanoparticles. You guys have a fantastic day, and I'm so glad you enjoyed it. I would like to do the harder topics. So if you have any topics you would like me to cover, all of my topics are viewer generated. You guys suggested this and you voted for this. So it's entirely up to you what I talk about. And I'm so glad I get to spend each Saturday morning with you here. And next Saturday is a 12-hour live stream benefit for Booleanator, also known as David, where we'll have various different people take over my channel and talk about all kinds of things. I'm so glad you guys enjoyed it. Thank you for being here. Sending squishy science hugs.